In this video, we're going to explore thermodynamics in radical halogenation. That mechanism is explored extensively in Chapter 8. Before we start, we have to get some wording down. What is homolysis? Homolysis is the breaking of a bond in half, with each atom receiving one of the electrons in the bond. Here's an example. If I look at the molecule HBr and I provide it with the correct amount of energy, I can cause the bond to pop in half, with half of the electrons going to the Br and the other half going towards the hydrogen, creating this. We've created two radicals, a hydrogen radical and a bromine radical. Recall that radicals have unpaired electrons. So that's an example of homolysis. Another question is, what is bond dissociation energy? Well, it is the amount of energy you have to put in to accomplish one of these homolysis reactions. The amount of energy, thermal energy, required to make a bond undergo homolysis. And where can we find these energies? Useful short form for bond dissociation energy is BDE. We can find BDEs on page 2 of test 3 at Moodle. Always use the most recent test that might have some updated numbers, and I think I have it handy right here. So here is a list of bond dissociation energies. Please don't memorize these. This is a table that will be given to you for your test. I need to find the bond dissociation energy for breaking H bonded to Br, and it looks like I found it down here. HBr, 368 kilojoules per mole. This means it takes 368 kilojoules of energy to pop open 1 mole of HBr bonds, according to this reaction up here. Now the question is, how do we use the bond dissociation energies? Well, in this chapter, we're going to use them to predict the energy of the two propagation steps of the radical halogenation mechanism, and this will allow us to determine which of the steps is the more important rate determining step, and then it'll allow us to answer other questions. So let me get the two propagation steps for the radical halogenation of 2-butene going here. Here's E2-butene. Bromine radical will abstract a hydrogen from E2-butene from the allylic position. The reason for this is the product is unusually stable due to resonance. So here is bromine meeting up with the hydrogen, and the other half of the bond goes to the allylic position here. I'll show right here. These hooks here show a bond forming between H and Br, each hook providing 1 electron for the bond. This third hook here shows the formation of the allylic radical as indicated here. Here's the new bond between H and Br, and here's the allylic radical. In propagation step 2, this is the radical that's going to react. I'm going to flip it over. I want it right underneath the first radical, so you can see the process for the next step's pretty much the same as the first one. That's going to grab a bromine from BrBr. Carbon radical provides 1 electron for making the bond. The bond between Br and Br provides the other electron, and the other half of the bond ends up on the other Br, creating these two products. Here we formed an allylic bromide and bromine radical, which should look familiar. If we look at the combined result of propagation step 1 and 2, we're going to see that bromine radical, which was a reactant here, is a product here, which makes it, in the overall process, called an intermediate. The allylic radical here is produced in Prop 1 and reacted in Prop 2, also making it an intermediate. And the combined result of Prop 1 and Prop 2 is the overall result of this reaction. When 2-butene reacts with bromine, it creates 1-bromo, 2-butene, and HBr. Now the question is, how can we use the bond dissociation energies finally? I've written a familiar number down here, but for some reason I've changed the sign. In this reaction we're making a bond between H and Br. Let's explore a simple fact before we move forward. I hope it makes sense that electrons, the only thing that stabilizes electrons, are protons found in the nucleus of an atom. So if you're an electron, you'd rather be between two nuclei than just close to one. You have more protons close by. You're more stable. That results in these two direct consequences. If you want to break a bond, you have to put in energy. Bonds are what hold things together. To get things apart, you got to pull them apart. Pulling is putting in energy. Making bonds is exothermic. You're making the electrons more stable than they were before. So, the amount of energy required to break H away from Br is exactly the same, but in the opposite direction of making a bond between H and Br. Now we have to find 3 more numbers. We also made this bond, and the category is more important than the molecule. This is a primary allylic C-Br bond. There is only one entry on the table for that, and we must find it. Primary allylic carbon bonded to bromine. Let's look. I'm going to run down the CBr column here. And the first entry, and I don't think you can see this, so I don't know if this is going to work. Look down this column, 1, 2, 3, 4, 5. The 5th entry is the only one in the carbon-bromine column that is primary and allylic. So I'm going to copy that number on our page. There's the number, negative 230. Why is it negative? Well, this is a new bond that wasn't there before. These electrons are more stable than they used to be before. That is an exothermic reaction. We also broke 2 bonds in this reaction. A CH that was allylic, primary allylic CH. Just do some editing here. And we'll go find that number as well. The CH column is on the far left of the screen. I'll read the entries going down in terms of categories for you. The 439 number corresponds to a methyl CH. The 418 number corresponds to a primary carbon bonded to H. Verify that for yourself. Don't worry about an ethyl group. Worry about the fact that it's primary. The 402 number corresponds to a secondary. 389 is a tertiary carbon. 444 is vinyl, and it's very difficult to get a bond to break with such high a number. And the positive 360 is the number we're looking for. It is primary and allylic. Do not use 357. That one is secondary allylic. Do not use 354. That one is tertiary allylic. So it's not just about being allylic. I will remind you, allylic is a carbon that is one away from an alkene carbon. So positive 360 to break that bond, negative 360 to make it. So I put positive 360 here. And that's the bond we're breaking. That's why it's positive. And BR is also breaking. Let's find that number quickly. The halogen numbers are on the bottom left of the screen. BR, positive 192. So we can calculate the change in enthalpy for prop 1 and prop 2 and compare them. And then we'll decide which one's the rate determining step, and I think that will be enough for this video. We've done all the hard work by learning these facts and consequences. The numbers we need to use are written as they are needed. So for propagation step 1, you need to put in 360 kilojoules per mole to break the primary allylic bond to H. And you're going to get back 368 kilojoules per mole, giving a delta H of negative 8 kilojoules per mole. Propagation step 1 is exothermic by 8 kilojoules per mole. Same thing for prop 2. I'll get the numbers down here. Positive 192 was for breaking BR. Negative 230 for making a primary allylic CBr. And if you're like me and you're trying to subtract a larger number from a smaller number, I have trouble without a calculator, and you're not allowed to use a calculator in this class. So what I do is I flip the signs of each one, put the big one on top, small one underneath, subtract. Remember, your answer has the wrong sign, so multiply everything by -1. You get negative 48 kilojoules per mole. Space here. And the overall reaction is easily determined by taking negative 8 and adding the next number to it, getting this result, negative 56 kilojoules per mole. Overall, exothermic reaction, which is a good thing. Now, the last thing we got to talk about is why is propagation 1 the rate determining step in this example. It has everything to do with this number being less exothermic than this number. And what does exothermicity have to do with reaction speed, you ask? Without getting into too much detail about thermodynamics, we'll do a quick review or preview for those of you who have not seen Gibbs free energy. And then we'll talk about entropy and how we can ignore it in these types of reactions. We can't always ignore it. And then we can use delta H as a predictor of speed. Here's the equation for Gibbs free energy, and it can be used to predict if a reaction is spontaneous as it's written or non-spontaneous. If delta G is less than 0, the reaction is spontaneous. And if it's positive, it's non-spontaneous. Once again, spontaneous reactions have... these are backwards. I have to apologize. Let's fix that. Negative delta G means you have a spontaneous reaction, and positive delta G means you have a non-spontaneous reaction. And the reactions we're studying, specifically prop 1 and prop 2, both involve a non-radical reacting with a radical to form a non-radical here and another radical. Let's do that again with the other reaction. A non-radical reacts with a radical to make a non-radical plus a radical. These are very similar types of reactions. So when we do have similar types of reactions, then we can say this: the more spontaneous reaction is faster, and the less spontaneous reaction is therefore the rate determining step, slower. This is good news. Our last thing we have to discuss is what is this delta S? Some of you are not familiar with that at all. It's a good question. So with delta S being the change in entropy or randomness of a reaction, if we see a reaction that creates more product molecules than there were reactant molecules, we have an increase in entropy. If we see reactions that create new gas molecules, they have large changes in entropy. In this chapter, this mechanism we just studied up here, neither of these is going on, so entropy change is negligible. And this equation here simplifies if delta S is 0 to delta G is equal to delta H. So our calculation here of -8 kilojoules per mole, combined with the fact that it's less exothermic than -48, says that our prop 1 is the rate determining step. Less exothermic means delta G is less spontaneous, means this is less fast. Another way to say less fast is slower. Rate determining step is the slower step. And this brings to a conclusion our discussion of thermodynamics and radical halogenation. And I hope you found the video to be useful, and I look forward to our next video.